of the trade-off. You gain space efficiency. Here's the other side of the trade-off. In order to find anything in this table, you may need to compute a large number of A51s. Say on your air interface, you're seeing this value. You didn't actually store this value in your table, so looking it up in this table returns nothing. You don't give up though, but rather compute A51 on it, reaching this value. Again, you look it up in your table and you find nothing. You keep computing A51 on it until eventually you do have a value that is stored on in the table, and that points you to the correct chain, and starting to compute that chain from the beginning leads to the secret key that generated the value you saw. Now, the longer these chains become, meaning the more space efficient you are, the longer you may need to compute A51 on it to find it. So that's the time-memory trade-off. Right? Now, this straightforward approach does not work for two reasons. First, just statistically speaking, you'll never cover all 2 to the 61 values in this table because remember the circle where all the values wrap around. Many of these chains will overlap in parts. And as you keep adding chains to an already large data set, chances are you're only creating more redundancy rather than adding more values. So that's the one thing that makes this impractical. The second is the speed of hard disks. For this to work, the chains need to be something like 1 million long. Now, computing 1 million A51 computations on a CPU is no problem. That's a split second. However, going to the hard disk 1 million times, asking, did you find this table? Did you find this in the table? Did you find this? That becomes a major bottleneck. So we need to optimize it statistically to avoid collisions as much as possible, these mergings of chains that only create redundancy, and we need to optimize it for the hard disk not to be a bottleneck anymore. Now, this is addressing the second point, the hard disk bottleneck. It's a technique called distinguished points. In distinguished points, you're only storing on the hard disk end values that match a certain criteria. In this case, the second half of the bits is all zeros. Now, instead of computing chains up until a certain length, say 1 million, you're computing them up until hitting exactly this statistical criterion, and then then the chain is finished, and you start the next one. By tweaking the parameters for this end criteria, you can again decide the average chain length, so that hasn't changed. But when cracking now and seeing a value on the air, you keep computing A51 on it until you find a value that matches your distinguishability criteria, and only then you go to the hard disk. So you've removed the hard disk bottleneck. The CPU time is still the same. That's distinguished points. A fighting idea in cryptographic circles is called rainbow tables. And rainbow tables do remove the problem of redundancy after collisions. Rainbow tables are the idea of computing a slightly different function in every link of your chain. They're all still derived from A51, but maybe with a different number XORed for every color of the rainbow. And when doing that, collisions such as these will not lead to the same chain anymore, since the function you compute on these colliding values is different in the next round. The only case where redundancy is still created is when the collision appears in exactly the same column, in the same color. But if these are 1 million links long, then you just decrease your probability of collisions 1 million times. And that's good enough for it to be practical. Now, as I said, distinguished points and rainbow tables kind of fighting as ideas. We just did both. We don't care that there seems to be an ideological war between them. we're combining them by computing a distinguished point, but not ending our tables there, but rather changing the color to a second color, computing up to the next distinguished point, changing the color again, computing up to the next, and so forth. For the optimization scenario that we wanted, 2 terabytes of hard disk, crackable in much less than a minute. Turns out that 8 colors is the optimum here. And this is how a tool called Kraken was computed. Kraken now is an interface into 2 terabytes of such tables. In fact, there's several tables, 40 for statistical reasons as much as for distributing the tables reasons. So 40 computers could be working on this at the same time. Now, I'd like to demo Kraken, but I have to explain a few more things before that. Let me go back to the Wireshark. This was the last packet that we saw from the phone in the already encrypted channel. And this packet has really no data in it. It's more or less a keep alive packet for another channel that's piggybacked on this channel. So this other channel, because there's nothing to say during the call setup, just sends a keep alive message at the end of this. In fact, there's several such messages through this channel. This one is one, and this one is one. So there's at least 3 messages that basically say nothing, meaning they are predictable. Even when they're encrypted, you know what these messages are, or what they're supposed to decrypt to. Now, knowing that, and in fact, I did of course, run this over a couple of my own conversations where I knew the key. Some phones just tell you the key if you nicely ask them using the right tools. So I asked them, I decode a couple, and it looks like that the conversation is almost exactly the same every time you make a call, with of course the exceptions of the caller ID is different, the channel that's assigned is different, but these empty messages are always the same. For instance, this 03031, 03031. So the last packet all seems to be the same every time. Now, given a call that's encrypted, and let me generate that data. So I'm again running this tool, but without giving it the encryption key. Given data from such a call, oops. This is just another way to present what you already saw in Wireshark. Here are the packets you can still decrypt. That's the unencrypted ones. There was 4 of them, I think, or 5. There are 3, 4, and then it stops. Now it can't decrypt anymore. So there should be 7 now, 7 packets that are encrypted. On this cell, with this operator in Germany, it's always 7. Maybe sometimes 8 if there's another system information messages interleaved. So there's 1, 2, 3, 4, 5, 6. This should be the last one, 7. Maybe it's 8 in this case, as I said. But this definitely is not 1 anymore. There's a 1 missing here. So it didn't properly decode. It's just junk on the same frequency. So this should be our last package. This is also the last packet, but in decrypted form. So this is from another call on the same cell. So you see that they're completely different because one is encrypted and one is not. However, if we XOR them, what we should get is pure A51 key stream. And that's exactly what we need to feed into our cracker. So this number is A51 key stream. It's a tool called Kraken. It was released last week. Oops. Now, I hope I'm not boring anybody. I just want to walk you through all the steps so you can actually repeat this if you wanted to. I want to specifically encourage everybody to do this to your own phone so you understand whether or not your phone operator has taken certain precautions that we'll talk about in a little bit. Now, what Kraken is doing now is it's loading the indexes of this 2 terabyte data set. They fit into, I think, 2 gigabytes of RAM. So there's a 2 gigabyte index and then 2 terabytes spread across 4 disks in this case. And disks turn out to still be the bottleneck. So cracking will take longer than we'd want it to be, and much longer than it would take if you had, say, fast SSD disk or just a bunch of USB sticks, for instance. So yeah, this did not start up. Huh. Let me actually move then this thing somewhere else. Yeah, there's two backends. There's one running on a CPU and one on a GPU for cracking. Now, since the hard disks are the bottleneck, the GPU isn't all that much faster than the CPU anyway. And after moving this file now, it will use the CPU. I think I need to be root to do the GPU attack. So here's Kraken, and we can just feed it with some key stream, and it will generate candidate keys. There's, again, because of all the nonlinearity, often keys or secret states that would match this, but that aren't actually the right ones. Now, I already know that the first round doesn't give a result here, but since we have 4 tries for just this one packet, and there's several packets, of course, I think the third one did actually crack this here. So let me already prepare the third one. So now I'm XORing again what should be in the packet with the data we saw over the air. The second candidate here. Kraken is still cracking. Yeah, on the CPU it does take a little longer. We'll be done soon with the demo and talk about a few mitigations. Now this could be running on my laptop. I just don't have a 2 terabyte disk attached to it. But if you had an SSD box or several